well, not totally that way, maybe one. But I sort of have like these A's and B's, which are just pretty good, you know, obviously. And then sort of a big hump of people that are really just not getting it at all. That's usually kind of what I have, and then it kind of drops off. Here we have, again, sort of not that many F's really, but we have sort of, we don't really have a curve on A, B's, and C's. We have like a, you know, sort of equal. So with the 8-point curve, which I didn't have to give, but I really wanted to make this. Oh, I don't mean, yeah, thank you for giving us a sucky dust and giving us some points back. I know. But the idea is we did have 15 A's, 12 B's, 13 C's, 3 D's, and 7 F's. Again, that, you know, obviously this is pretty good. And again, if we're in this range, you got to figure out what's going on. You've got to sort of work something with me or something with your life. You got to figure out how to correct this pretty quickly. This range, hey, we're in a pretty good range. I think basically everybody can in this range can do better as well. And so we can get more A's and make sure a lot of C's can get up to B's. Again, if you're having trouble, I've just talked to people again. You know, there are people, you know the material, you've been studying, but those critical thinking questions, the multiple choice type kind of questions throw you off. And again, is that life, multiple choice questions?
No.
No, it isn't. But is it something, a hoop you have to go through here and then entrance exams, all that? Yeah, and so if you get better at that, it's going to help you, and it is part of this course. So all I can say is try to work on that. I understand it's making people very rigid, and you know, you're going to learn a lot more than that, but it is what it is, so to speak. So that's that. Lab tests, though, very literal. Basically, we reviewed last time in Wednesday's lab. Today, we'll go over after our lab, which is a blood lab. Won't take that long. We'll go over, you bring those sheets in, you'll know exactly what's on the test. Exactly what's on the test. And that's 60 out of 60, okay? I promise you that. There's no critical thinking questions on that. It's simply, can you do a molar conversion? Okay, can you fill in that osmolarity tonicity chart? So that is going to be done, and I haven't added just the lab points yet of just the labs that you attended that you're getting 10, 10, 10. And that's going to, again, add you some. I like to have done it on the weekend to make people feel like, okay, well, this is where we are, but I left my sheets here. So the next couple of days I'll do that, and there'll be a couple more like that. So, you know, you can, you know, you don't have to like panic if you're not quite where you want to be yet. We have plenty of tests left, but yeah, if I, Lynn, or somebody can help you on some of these multiple choice, going over them, that would be good. Any questions about anything coming in? Show me, not Google Earth, tell me, what did we do last? Because I got these 4 classes or 3 classes. Where did we leave off? Anybody know?
I think we left off the defects of
We right at that drug, or did I? Right at digitalis, okay. So we did all the heart valve stuff. Again, I'm going to probably get us to listen to that stuff soon. I didn't do it in lab. Let's get us on board here. We went through that. Okay, so we didn't do the action potentials yet. Let's get us on here. Just get to the end of this, because then we went to the drug. The whole idea was we were looking at the cardiac contractile cells. We were looking at basically how it contracts, you know, like we had skeletal muscle contraction. And again, it was very similar. It was very similar to skeletal muscle contraction, except for the fact that we used extracellular calcium as well for the cardiac. So calcium plays even a greater role in cardiac contraction than skeletal muscle. The more, we have this on the next slide, on this one. Basically, the longer we get calcium in, and the more there, the greater the force of cardiac contraction. And that's going to matter for cardiac output and blood pressure, which is the chapter coming up. So it's pretty important. Now overall, the idea then came that the differences were at the beginning and the end. And that's what you're going to have to know. You're not going to have what are the 10 steps of cardiac contraction. Beginning, we're using extracellular calcium, which allows calcium to be released from the sarcoplasmic reticulum, and you have a lot of calcium. Everything else is about the same. And the end now. Not only do we do calcium ATPase to put it back in the SR, like skeletal muscle, but we also have to pump it out since we took extracellular calcium. And the key with this is we do it in 2 steps. If we would have done the other part of chapter 5, we would have been introduced to this concept, but we're introducing it now again. So we have this idea of active transport, requiring energy. Anytime you're transporting something against its concentration gradient, you need energy. So when you're using ATP directly, it's primary. And so to set this up, we have our famous sodium-potassium pump, pumping sodium out and potassium in. But because of that, we're going to use that same idea. We have low sodium. And so by having low sodium now, we've created a concentration gradient. We've put water in the dam. That's potential energy. So how we're going to use it, we have this transporter here that as sodium goes down its concentration gradient in, it's driving calcium out against the concentration gradient. We want to get all this calcium out so that it doesn't keep contracting. So it's primary and secondary active transport. Basically, this doesn't happen unless this does. This creates the low sodium. That allows basically the sodium not to run down its concentration gradient, driving calcium up. This puts water in the dam. If you open up the dam and the water runs down, it can be used to drive turbines, electricity. That's really the concept here. And what's nice is, bless you, you don't have to be afraid to sneeze. I always fear when people are like, they like go off their head, okay? Just let it out, okay? Well, contain it, but let it out. Did I just embarrass you? I'm sorry. I've lost my train of thought, so we'll just continue. So that's where, again, this section, we're going to be talking about really, real things as far as drugs and sort of some pathology. So I want to introduce one drug since we were doing this, digitalis. And again, this is sort of what we ended up on, so I want to repeat it. So this is sort of an interesting drug, because what it does is it inhibits this important pump, which is in every one of our cells. And with that, so the idea of this is, again, you sort of play the game that I wanted you to play in the first question on that test. What will happen? All right, so the idea is if we're not pumping sodium out, we're going to have sodium stay there. That was actually the answer to question 1. You're going to accumulate sodium in the cell. But in this case, the idea we're looking over here, if we're not creating a gradient, we're not going to be able to have this sodium-calcium exchange as much. The gradient, it's like we're only putting water halfway up the dam. So because we have too much sodium here, we didn't get rid of it, this doesn't work very well. Calcium stays in longer in the contractile cell. But that leads to, and they call it, higher inotropy, but increased contractile force. Because the longer calcium is in, the more contractile force there is. And so again, you can kind of see when it's used. If your heart simply is not working efficiently, if we're not getting enough, the muscle working strong enough to get cardiac output and blood pressure, etc., we can take digitalis. Obviously, there must be some pretty careful dosages because it seems like a pretty intense drug. But basically, that's how it's going to work. It's going to increase calcium levels in because this isn't working as well. Increase calcium for a longer period, increase contractile force, pumping out more blood.
It also increases the sodium inside the cell, yes?
And it increases the amount of sodium inside the cell as well. Which might actually have another effect as we go on of sort of slowing, it might be not actually as fast, the heart rate, but it's going to be basically a more contractile force. So, action potentials. Where are we here? Action potentials. You're walking pretty well. Yeah. So, we had 2 types of cells. We had contractile cells, which were the 99% that we just looked at, the inside of them. But we also have What?
Relaxo.
Pacemaker. So we have two types of cells. In fact, let's just go back to my picture of the heart. When you look at the heart, we have two basic types of cells, and they're going to have their own action potentials. But we've just done an action potential, so it won't be that bad. So 99% are the actual contractile cells that we just looked at. Those are the ones contracting. But the 1% is sort of these cells in dark purple. That's going to be the ones which are autorhythmic, pacemaker. They're going to reach out, basically reach threshold and then spread the signals out through gap junctions to the heart to cause contraction. So that's the 1%, that's the 99%. They have different looking action potentials that we're going to look at and learn. So, when you look at this picture, sort of remember, hey, this is all cool. Okay, fast potassium channel, slow potassium channel, up arrows, down arrows. I don't like explaining it this way, but we're going to look at this picture. The key with this is, for the contractile cells, we're going to have a depolarization like we're used to seeing. And usually, of course, we have a quick repolarization. This time, we have a plateau. So I want to describe three regions of what's going on here. And the key, the question is, what's causing this plateau? This plateau being this extension of, instead of having the action potential only a couple milliseconds by coming right down, we're extending it, creating a plateau so that it lasts a couple hundred milliseconds. We're going to say what causes this and why. So the plateau, what causes this and why. So we need our circle of life. We're not done with him yet. Okay? Inside, we know negative. It doesn't have to be negative 70 anymore. This is negative 90. I don't care. But that's the same basic here. And the outside, sodium and calcium, smiling. It's like my time. Okay? And chloride saying, oh, well, I'm on the bottom again. But calcium, you can see, is playing a role. And the reason, and we're going to see this when we get to the next chapter, there are things called calcium channel blockers for heart conditions and blood pressure conditions, and you're going to see why they're so important, because it's involved everywhere. So those are the ions. And so we're going to look at what causes the depolarization, 1, what's causing the plateau, 2, and repolarization. Now, luckily, what usually causes, with the nerve, the depolarization? What channels? Sodium. Same thing. Okay? So, they have arrows, if you're just curious of, this means it increases sodium permeability, which is like opening channels and sodium flows through. That's why I just don't want to worry about the arrows here. I want to basically have it the same way. We're going to open up sodium channels. And of course, sodium goes in. Just like we did before. So that's easy. Now usually, and in fact if we put number 3, part of it, what's usually causing the repolarization? Yeah.
Potassium channels.
Potassium channels, and potassium is going out. So what we have here is, we can kind of look at this. We start to do that with potassium, but then we have this idea that, okay, potassium is going out, and that's making the cell more what? Positive or negative?
Negative.
Now, if we want to keep it, we want to extend this so it stays kind of where we were at, we need to counteract. We need to counteract losing positive. And we can do that by having calcium come in. Positive is going out, calcium's coming in. That's what's creating, and they have their way of arrows, but that's what's creating this plateau. We're sort of equalizing the charge to extend this action potential. And so the way I'm going to write it basically is why what's causing this main plateau is that fact where we have potassium. You can say open, but right now they open obviously. Potassium is flowing out of the cell. It's sort of equivalent to the amount of calcium going into the cell. So we're keeping at a depolarized state to extend the action potential a couple hundred milliseconds instead of 2.
So however much potassium goes out, that's how much calcium goes in?
Yeah. you know, I mean, again, I don't know if quantitative it's exact, but it's creating because it's sort of different charges, right? But it's creating it so that the overall membrane potential is staying kind of where it is. So it's equilibrating the amount of charge to extend it. Now, what happens at 3 is, well, you have this idea of calcium channels closed. Now, again, they have the idea that there's fast potassium channels and slow potassium channels. So these are the ones that open here. I simply don't care about that point. Okay, I mean, I want us to get. I mean, you know, it's real. There are different types of channels, but you know, I want to get us the main point here. So I'm not going to talk about different ones. I'm basically this one's causing. This is again sodium in. Okay, this is again potassium out. Equaling calcium in, then calcium channels close, and potassium channels are causing potassium to go out, repolarization. So don't worry about fast or slow. Basically, we're using potassium channels. On the plateau region, it's being equalized by calcium coming in. Once those things shut, potassium continues to go out, and you repolarize. You can see we don't hyperpolarize too.
So the 3, it's calcium channels closing.
Yes.
And
Well,
out.
and potassium continues to go out, exactly.
Okay.
Yes.
Did you say we're not worrying about the other ions at this point?
What do you mean the other ions?
Like anything that would affect it, like
No. Because
like fluoride or
no, and in fact, that's an important point. Like if I were asking again the same question, how would if we used a chloride channel blocker, how would it affect this? It doesn't, right? The only ions, now we have 3 of the 4, but the 3 ions that are affecting it now are sodium, potassium, and calcium. Chloride has no effect over here. Are we good with that? So let's get the other one. Oh, I'm sorry, I forgot to tell you why. So why would be, looking at this, if you looked at what we did last time, we talked about skeletal muscle. We had a action potential, and then followed by the actual contraction relaxation, which takes a lot longer, 100 to 200 milliseconds. This is a fast switch, so it's pretty quick. Now the idea was, what if we fired more action potentials here? What would happen to the contraction? It would increase up to the level of tetanus, right? Okay? Because, again, you keep firing them, more and more cross bridges, and finally you'll reach tetanus. Do you want your heart to be in tetanus?
no.
No, that wouldn't work out. So, cleverly, this is pretty clever, right? Cleverly, by creating that plateau and extending the action potential, it basically equals the cardiac muscle contraction. So that the next action potential that will happen will be when the cardiac muscle is fully relaxed to allow it again to fill up and pump. That's what we need. We can't have it so it's like this, or else it won't fill up and pump the next one. So you basically, that's sort of the purpose of the plateau, to prevent cardiac tetanus, okay, to make sure the cardiac cells do not get stuck. So we actually, that's why we have to keep this at 100 to 200 milliseconds, because that's how long it takes for the cardiac muscle to contract and relax. So you see it's extended the same. Clever. So that's what causes the plateau, and that's why, to prevent tetanus.
So just to prevent tetanus.
Yeah,
Okay.
and they have that. I don't know why I have that revisited. Yeah, we'll skip on that one. Okay, the other guy, pacemaker, the 1%, SA node, etc. They're going to be over here. They look something like that. My picture's not that bad. These pacemaker cells, I'm going to again define this in 1, 2, and 3. But the first thing, and we can kind of see this, again, a different negative voltage, we don't care, but, for these cells, they don't rest until you're dead. So we're not going to call that a resting membrane potential. We're going to call it a pacemaker potential. So again, you're going to see that once we do this, again, that it's not really at rest. It's going to immediately start kind of depolarizing the threshold and keep going like that. That's how we're creating this pacemaker idea. So 1, 2, 3. The 1 is what's causing the slow depolarization of threshold. 2, what's causing the major depolarization. 3, repolarization. 1, 2, 3. So 1, what's causing, so 1, 2, 3. What's causing the slow depolarization of threshold, again, you don't need to remember the numbers that are threshold, are called funny channels. You can see they're IF. And they are called funny channels because they just operated funny when the people studied them. I'm not making that up. That's what the book says, I believe. Now, what these channels are leak channels. Just like we saw with the nerves, the nerves and the basic creating the resting memory potential. They're linked to the same ones, sodium, potassium. Look at our circle of life. Okay, when we look at that, if we're leaking, sodium's going to leak which direction? In. Okay? And potassium is going to leak. So who's winning this battle? Sodium, right? The idea, and that's the idea, just go back to this. You have this idea, we're getting more positive. So positive is leaking in, positive is leaking out. Well, more sodium must be leaking in, the potassium leaking out. That's how we're slowly getting up to threshold area. So they're leak channels, but somebody's winning here. More positives coming in, more positive is leaking in. Where am I here? More positive is leaking in than leaking out.
Is that like the sodium potassium thing?
Not the pump. Remember that even in the resting memory potential, we said there were two things that happened in that for the resting. We had the sodium potassium pump pumping sodium out and pumping potassium in, and then we had the leakage of sodium back in and potassium out. But potassium won that battle, right? That created the resting. In these cells, it's the other way around here. The sodium wins. So more sodium, and again, I can make it, the cell is more permeable if we really want to be, sound more impressive. More permeable to sodium. Again, I like to have it make other sense to me. More sodium leaks in compared to potassium leaking out. Again, this leaking idea is we're changing the permeability, which is basically saying the same thing. So remember both words if you want. Yes?
We're just starting over there from one resting, just so that you can show a pacemaker.
Pacemaker does not have a resting potential. Okay? We call it a pacemaker potential because at this potential, these leak channels start doing this. Okay? Once we get back down to this, and we'll show you 2 and 3, they start doing it again. So it's never at rest. It's always leaking. It's just that this takes precedent once we reach threshold, and then we're going to be at this minus 60 again. These leak channels are going to work that way again and keep going.
But contractile is at rest.
Yeah, that guy's at resting, okay? And basically, then you're just going to have sodium in. So that one's just like skeletal muscle and nerve. This is the one because this is automatically, without any nervous system input, causing this pacemaker contraction.
Just to confirm, when you're talking about leak channels, it's going to go against its gradient regardless.
It's going to go down its gradient.
That's what I mean, not again, down, to the other side. So basically, when we were talking about the resting membrane before, we're saying that the cell was more negative because Ka was permeable and coming out of the cell, making it more negative.
Yeah, exactly. It was more permeable at that state in those cells to potassium. So more. That's why this is just the opposite. It's more permeable to sodium, and so it ends up becoming more positive. Now, it says, but we're going to ignore this little detail right here, that at the very end, we get some calcium channels opening to get a positive. But really, again, I like to sort of get the basic idea. And so, but this is something we've got to remember. So far, every depolarization that we've done has been sodium. Guess who's about now? this. I'm going to do it. Calcium channels open. Again, calcium goes in. That's causing the depolarization in pacemaker cells. So number 2 is you're almost getting dizzy with calcium so far. Calcium, we're not done with it yet. So calcium channels open. Again, calcium in. That's what's causing this depolarization. Luckily, what causes repolarization so far? Stay the same, potassium. So that part's okay. Potassium out. So number 3, repolarization. Again, whether I write potassium channels open, but potassium goes out. Okay, you can write the channels open. And then again, as soon as we reach the receptor potential or the pacemaker potential, this happens again. Okay, and that's why it's going to be rhythmic. And this again, this is in the pacemaker cells that will then spread out via gap junctions to all the contractile cells to cause contraction. And then it's going to happen again and again and again. That's the idea of these pacemaker cells. They're all these going to be, without even any nervous system input so far, all these reaching threshold, reaching X potentials, and then causing this pacemaker of the heart, basically. So right away we do it again. So again, 3 steps here. Ignore this extra little step of some of these channels here. So we got this, this, and this. So we have that we're going from, we're basically going to reach threshold by these funny channels, these leak channels opening, and more sodium's coming in, the potassium's coming out. We reach threshold, boom, lots of calcium. So calcium channels open, calcium comes in, okay, they close, potassium open, and then we have repolarization, and we start it again. So, and I'm hoping you're starting to get this idea too, that, this is not that bad for you guys. You kind of get the idea. We've already done X potentials. This is like sort of just a variation on the theme. But you've got to know the difference between the 2. Any questions? Again, all those words, of course, are there. Let's look at this again. We're going to do EKGs today. This is going to kind of come up on this. But when you look at these pacemaker cells, the conduction of the heart in the dark purple, I just want to, we went through it once. We'll kind of go through it again and a couple more times probably over and vary it. So when we look at these, basically, these pacemaker potentials, they are happening in all of these cells. But we're going to see that usually the pacemaker of the heart, the one that does this the fastest, and so it spreads, is at the SA node. And so the SA node is going to be firing. It's going to be going quickly to these internodal pathways so they can then spread to the atria to cause contraction. This is kind of like, what's going to cause the contraction. But the signals are SA node, internodal. And then at the AV node, and we're going to see this on the EKG today. At the AV node, it slows down a bit. Okay, it's going very rapidly through these. It slows down a bit, and we call this AV nodal delay. And we're going to see it on the EKG. The reason was that we want the atria to contract, and then the ventricles contract. We don't want them sort of competing with one another, or one just to do it and the other one sort of sitting there. It's atria contract, ventricle contract. Atria is basically topping off the ventricles, and then the ventricles pumping it out. So by having that slight delay, and we're going to see it again on the EKG that we'll see today in class, and we'll actually do EKGs after we do our lab test. You'll see yours. But there's something called an AV nodal delay. Then it goes rapidly through the AV bundle branches, Purkinje fibers, and then from the Purkinje fibers, it spreads to the contractile cells of the ventricle, bottom up, so that we can squeeze from the bottom, which makes sense. And that's sort of the conducting of it. All of those cells do this, but at different rates, at different rhythmicities, naturally. This is sort of a cool picture, by the way. You can kind of see both of these here, that when you're looking at sort of the cells of the SA node or any of them, they're going to be creating these autorhythmic potentials that then will spread out to the contractile cells, which will cause them to contract but use these action potentials. So it's kind of a cool picture. So, bottom line, all of those cells that we just mentioned have this pacemaker type of action potential. But the SA node, without, and I say basal in the sense without any nervous system or hormone influence, which we're going to add next. So just, you put that heart out here, okay, and just look at it. The SA node has the highest rate. And so the SA node will normally control the heart rate for us. And without any nervous system or hormones, it would be going at 90 to 100. The AV node itself, if it's not being influenced there, basically can go to 40 to 60. And we'll see, actually let me just show this slide right here, that's enough. If the AV node isn't working, the SA node is not working, the AV node at 40 to 60 is enough to kind of keep us going if we're not running a marathon. Okay? Obviously, you want to fix the problem, maybe get a pacemaker, but 40 to 60 will do it. Now, if that's not working, if we're further down, these guys only are at 20 to 40. Okay? They're doing the same thing, but it's much slower. This isn't enough to actually, get enough cardiac output. So you definitely need a pacemaker. This is just a funny picture I got from some other book. Don't take it too seriously, but it's kind of showing, they use a different number here. They use miles per hour, but it's basically showing that the fastest one, SA node, sort of leads the train. If it's not working, the next one takes over, which is the AV node. If the AV node's not working, the next one will take over, some of the bundle branches or the Purkinje fibers, but it's much slower. This picture though, and this is again just in, I don't know if I even put it in your handout, it's a PowerPoint. It's just, we're going to show some bad EKGs, and when we're going to sort of have this fibrillation, there are things called, like here's Purkinje fibers. If you start having in your ventricles these Purkinje fibers just firing on their own, like you can see 140, that's what's going to cause sort of your heart not to work. It's going to basically have, we'll see on the EKG, you're just going to have cells all around your heart starting to contract, but basically not have a contraction of the heart. And you'll see this fibrillation that you need sort of a defibrillator. So that's just showing that. But basically it's this idea I'm trying to get here. Now, is your heart going at 90 to 100?
No.
No. So the idea will be the nervous system will influence this. And this becomes, and let me put this picture up first. This becomes extremely important for the next two for the next two chapters. We're finally getting to the autonomic nervous system, sympathetic and para. See how we have cardiac and smooth, because we're going to talk about arteries soon. So, and here's sort of the idea. Sympathetic basically will increase heart rate. And again, they have this up here, and I have that up here. The idea is, if you increase permeability to sodium or in calcium, that's going to make this more likely to fire, and therefore it's going to be more rapid, heart rate. So that's sort of what sympathetic does. It increases the permeability of those ions so that we have a faster heart rate. You're going to need to know, as we'll see next week, you need to know the neurotransmitters involved, norepinephrine. So sympathetic is going, and we'll show you where, is going to increase heart rate by adding norepinephrine to the heart, and that's going to speed it up. While we're speeding it up, epinephrine, sort of adrenaline is for the old name, from the adrenal gland also does the same thing. So if I'm up here talking about exciting things and I'm moving, I'm speeding up, right? So I've got a little more sympathetic stimulation and probably some epinephrine speeding it up. But you've had a long day and I don't know if I can listen to Mike anymore. Okay, you have parasympathetic hitting us, and so remember both are going on, but we're turning that up. So parasympathetic releases acetylcholine that in this case actually will decrease heart rate. And we'll show you what receptors and why. It decreases heart rate. Acetylcholine to the neuromuscular junction caused increased contraction. Here, it's going to be the opposite. We're going to decrease heart rate by doing the opposite. Basically, making sure calcium doesn't enter as much and increasing potassium going out, kind of hyperpolarizing the cell so it doesn't happen as much. So we're just, they're still having this rhythmicity, but we're changing how often it happens, and that's heart rate. Here we're hyperpolarizing it to make it less likely to happen, to slow us down. And by these methods, we're going to do the opposite. Just partially depolarize it, speed it up. And I want you to remember, we're going to see this over and over, that let's say we want to increase heart rate. If we want to increase heart rate, you want to keep thinking, and I'll sort of just put both, and we'll see this, we're doing both. Okay? We're not just saying, okay, let's just add more sympathetic. We're going to add more sympathetic stimulation, but what are we going to do to pair it?
Decrease.
Inhibit the inhibitor. Okay? We have a given amount of acetylcholine going on inhibiting it. If you decrease that, that speeds it up. It's the same concept. Two ways to speed things up. You increase the activator or you inhibit the inhibitor. And that's going to be very important. So think about that when you're sort talking about increasing or decreasing heart rate. It's always going to be both things going, just tweaking. Does that make sense? And again, you can see, by the way, we're going to do EKG, that this thing shouldn't look as bad as it once did. Okay? We kind of had this whole idea, now we're starting to get this in play, and it's pretty much you're learning all this, pretty well. Okay, let's have some fun. So, I don't know why I have this on. So EKG, we're going to use the board here. Again, we've got words here. Basically, what an EKG is, we're not going to stick a probe right into your cardiac cell and look at those action potentials. And so what we're going to do is kind of like we did with the EMG for muscle. Basically, as the heart's contracting and electrical signals are going around it, they're releasing ions, electricity, that we can put probes on the surface, amplify, and get the electroactivity. Just like the EMG. But it's an EKG, electrocardiogram. So we're doing that. It's the electrical activity. The key with this is, I'm going to redraw this. There's actually 6 things right now that I'm going to want you to know about the EKG. The cool thing is we will measure our EKGs in lab once we get through this test.
Is the 6th one not on there?
The 6th one's not on there. And I'm going to tell you the 6th one.
Called ECG?
The ECG, EKG are the exact same thing. It's like, I don't know if it's true. It's a good question because it's like, yeah, it's like, why are they have 2? But they're actually the same thing. Depending, I guess, if it's German or not or something. Okay, so I'm going to draw this. Okay, we're going to do a lot with EKG. I mean, we're only beginning on this. And I have some abnormal ones as well. So the basic waves that you're going to see, P, Q, R, S, and T. And what we need to know about them is actually what's up there. So first of all, okay, well, let me just say this. P wave represents the sum electricity caused by depolarization of the atrium. The electroactivity going through the atrium. Now, this is not depolarization, repolarization. This is not sticking sort of a probe in and looking at that. This is just by where you place these I guess I should say probes, I can't think of the word. But where you place the probes that you put on is going to basically get a wave of a signal. So don't think of this as depolarization, repolarization. Just think of this as activity. And so this first P wave represents the activity by depolarization of the atrium. Now once the atria depolarize, they're going to send signals to the ventricles. And the QRS complex represents that. Depolarization of the ventricles. Much bigger because ventricles are bigger, create more electricity. Okay? This isn't contraction yet. Contraction is going to basically follow these things, and we'll show some of it. But basically, this is just measuring the electrical activity of the signals going through the atria, and then the ventricles, and then the T wave you're going to see represents repolarization of the ventricles. And then you have your next heartbeat, and the next one. So PQRST, depolarization atria, depolarization of the ventricles, repolarization of the ventricles. Those are the 3 parts of the EKG here, as far as the electroactivity. And you're going to see that on your cell. Now, underneath, I'm going to draw my intervals. You know, there's different intervals and different books have, and I even erased it because I don't care. You know, I'm going to show you some cool ones. You know, QT, PR, we're not looking at those. We're looking at mine, which are more interesting. Right. Okay. From the end of P to Q, we had atrial signals, then ventricle signals. That's going to represent the AV nodal delay. Remember, there's a period in between when the atria signal's happening and the ventricles, so we can have separate atrial contraction and ventricular contraction. There it is. Okay? Basically, the end of P to Q. That's AV nodal delay. We're going to see, if we have a heart block, how when these aren't communicating well, this interval starts getting differently. So, because we're going to look at some abnormal EKGs in a minute. But that's the first interval I want. AV nodal delay, the end of P to Q. That's sort of, you know, space of time of, you know, between the communication. You'll see it's a millisecond or so. Now, when these signals go through, you know, the atria, it's going to cause then systole, contraction and relaxation. I'm not going to put the atria on because it just messes things up. I want to show you, and these are the other two, what corresponds to the ventricles contracting and when they relax. So, here are mine. Again, you're looking what I'm doing. Different books vary slightly. I'm putting R, which is the peak, to the end of T. Some books kind of put them really close, but I'm putting it at the end. So as signals spread through the ventricles, it's going to be followed by ventricular contraction. And that's the period, basically, from R to the end of T, once it resets. So R to T, again, this is R to the end of T, is going to be ventricular systole, contraction. Systole, which is contraction. And I want to put this will make sense as we go over the next week or so too, kind of what's, you know, to remind us what it's doing. When it's contracting, what's it doing to the blood?
Pushing it out.
Pushing it out, pumping it out, ejecting it. So we'll put ejecting blood. Now, as soon as it's done that, what does it need to do? Relax. Diastole. So from there all the way to the next time it's going to contract, so from the end of T all the way to R, remember this is P, QRS T, that's going to be ventricular diastole, which is relaxation. Now what's happening then with the blood? Filling. And we're going to see that's important. The more blood we put in, guess what? The more blood we can pump out. It's going to be coming out as all. So ventricular diastole relaxation, you want to realize this whole period of time, this is filling with blood. It's going to be very important. And so those are the 6 things right now. We're going to add a few things in a minute. But when you look at an EKG, you're going to practice this, although it's not an essay question. Practice it over and over so you get it. You're going to have the waves, depolarization of the atria, depolarization of the ventricles, repolarization of the ventricles. Then these 3 segments, AV nodal delay, and then this whole heartbeat is in contraction and in relaxation. So systole is R to the end of T. Make sure you have that because, again, sometimes they vary in text. One. Let's see where we are on this one. And then, as soon as it does that, it's going to relax, diastole, fill up with blood, all the way to the next time that it contracts, which will be at R. So what do you think? Any questions?
What do you mean by 6?
Say it one more time.
What did you mean by 6 then?
6 things because we have what the P is, what the QRS is, what the T is, and then AV nodal delay, systole, and diastole. So far 6.
So AV node delay is 4 in the TR interval. Is that what you're calling?
That would be 4. It's the 4th thing that I'm talking about, or what?
Yeah.
Yeah, and the one that's not up here right now.
Okay.
Because I got like these 5 things up here.
Yeah.
But I didn't put this one on the slide, right?
The end of chapter.
So the end of T to Q, that's the period of AV nodal delay.
4 to 6. 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 4 to 6
And we're going to see something go wrong in a minute on a bad EKG. Yes.
Will it make any sound?
We're going to put some sounds. We're going to show you. You know, I don't know if this electricity makes sounds. I don't know, but we're going to correlate heart sounds with the EKG. I don't think it makes, but I don't know. I mean, because we didn't listen to the EMG one. Maybe it does make some sort of electrical sound, but really we're looking at correlating the first and second heart sound. Did you have a question?
So the diastole is a longer period.
Yes, that's going to be very important because we're going to see this is very important that the time, this is filling the entire time. And so diastole is really almost twice as long as systole. So when we actually do blood pressure, we're going to take that into account. And again, the longer that is, the more blood that comes in, the more blood that's going to come out. And it's going to be stroke volume. It's going to become really, really important this next week. But right now we're just introducing where this is.
I don't know why I'm not, like, I'm trying to put together the 5, I guess, steps with what we have here.
Yeah.
For some reason, with the TR interval, why is that listed before the RT? When according to
This is not like an order of things.
Oh, okay.
Yeah, this is just me writing the 6 things down. No, this is not an order of things.
Okay.
I guess it would be better if I put it the other way around, because it is
According
first,
to
right?
that.
Yeah, and this is sort of when we're doing it. We're looking at this and then this usually, right?
Okay, so let me.
So, let's look at some abnormal ones. I didn't like the book per se, their little page of abnormal ones. This is relatively new, luckily you. And part of this, by the way, this I want to mention this now too. When you look at, I might have mentioned it, but see, right now with 3 classes, I get confused on what I've said, so I might repeat myself. On the study questions for this section, there's some which you're going to see that are on comparing smooth muscles that I'm not going to lecture on, but it's in the book. You'll see these questions. And then I have you actually sort of look up a couple of EKGs from this one site that I'll show you. But I've actually put them all you need to know on, and a couple more. So we're going to add study questions that you're going to need to know all of these. Did I redo I know I redid the PowerPoint. I redid the handout too, right? Yes. Okay. So here's what we need to know. Here's some abnormal EKGs, and we're gonna actually expand on why these drugs work. But the idea is, okay, here's what a normal EKG looks like: PQRST. So bradycardia, slow heart rate, under 60. And you can see when you look at the R to Rs, they're further apart. That should make sense. That's a slower heart rate. Now, again, bradycardia under 60 might mean you're an athlete. Okay? I mean, it's not necessarily bad to have a heart rate under 60, but if it's chronic and it's causing a problem and you're not getting enough blood out, you might have to do something about it and speed it up. And so, basically, these are 2 drugs, and we're going to talk about them a little more specifically soon. But, if you give atropine or epinephrine, that's going to speed up heart rate. We already know about epinephrine, we just mentioned it. Again, that's like adrenaline. But atropine is also something we'll talk about. So, that will speed up. Tachycardia. Heart beating too fast. We're going to show you why. And again, I know that I'm sort of ahead of the game, but most people, if people heard of beta blockers, we're going to show you exactly why, probably the next lecture, but beta blockers can slow heart rate down to get us back to normal. So, too slow, too fast, this is what we can do to try to restore normal EKG, normal heart rate. Any questions about those? Next. How many people have heard of PVCs? Premature ventricular contraction. I mean, did you watch ER when it was on, all these shows? I mean, there's not as many medical shows on anymore, but you would just hear all this terminology. And so I'm like, okay, what's a PVC? And what it is, I have the bullet points up there. This one I don't have kind of a real picture of one, versus the other ones. But basically what happens is that normally, again, you have, and we can even do it here, you have atrial signaling to ventricle signaling. So you have atrial contract, and then ventricle contracts, and then rest all the way until the next time. But what if during this time, some of the cells in the ventricle contract on their own? And that's what a PVC is, premature ventricular contraction, that's somewhere in the middle here. Instead of waiting for the SA node to signal, some of the cells within the ventricle basically cause contraction. And so, is the heart completely full at this point? No, and that's sort of the idea. I mean, it looks a little weird the way it is here, but the idea, if you're contracting on your own in the middle, you're really not ejecting anything. I mean, or very little, so it's not very efficient. And if you just get, if you have, once in a while, you might have, all people might actually have one of these, but then you get restored and everything's okay. But if you have, a lot of PVCs happening, then you're going to have the idea where you're simply are going to basically not get enough blood out.
So is that like a heart flutter?
Flutter. I've got to look up flutter.
It feels like it feels like it just beats really hard.
I mean, I literally, because I was looking up, I mean, this is like a whole complex thing, and flutter, I have to look up flutter, because flutter actually has a specific idea, so I don't know if it's like a heart flutter.
Have you ever had one?
I hope not. But I'll look it up and find out and tell you, and tell everybody too, but flutter was something very specific, I don't want to make a mistake on what I say.
So on a normal heart, the R is where it's contracting?
It's basically, because the QRS represents the signal, remember looking at the signals? That's the signal spreading through the ventricle. And as soon as they're spreading, we're going to initiate contracting. And so from basically, the signals are spreading this whole time, but basically at R, basically is when it corresponds to the actual contraction. This is the electroactivity, and basically as soon as that's kind of, you saw that in the picture of the purple, that's sort of when the heart starts contracting. So right at R until the end, about the end of T. Yes?
So that means P would be the signal for the atria?
Yes. And so we didn't put it up because I don't want to confuse it, but it's like right here, the atria is contracting. Okay, but you can look at it, but I don't want to like add something to that. But that's exactly right. So these are this is the events that correspond to electroactivity is what we're putting down here. This is just the electroactivity. Yes.
So during PPC, you don't have a P wave?
So, but it will return. But yeah, that's the idea. You basically you're not having you missed the P wave, right? You had QRST, and then all of a sudden you have a contraction of the ventricle. Then of course then you might get it back if it's okay. And so yeah, you've lost communication and it's just beating on its own. And the trouble is it's not waiting to fill. So it's sort of just you're squeezing out not enough blood, not enough cardiac output, not enough blood pressure, etc. But again, if it only happens once, but I'm going to look up flutter. It's something different, believe it or not. This is like crazy. But heart blocks, and I'm going to show a particular one. In heart blocks, basically, the communication between the atrium and ventricles and the AV node, which we're showing here, is somehow being blocked. The cells of the AV node are damaged. So you've got kind of a short circuit as the electricity is going through. That's what a heart block is. You're losing some communication. Now, there's like first degree, second degree, third degree, so it depends on how bad it is, and we're not gonna go through what's first degree, second degree, third degree. You can do that in some advanced class. I just want you to get the idea of what a heart block is. That all of a sudden you start, and well, I'll show a better one because this is the one I want you to know, and this is the one I want you to be able to identify. It's called a wiki block because it's sort of cool. I mean, it's easy to follow. So look at this idea of a heart block. Again, I have it again. You have this idea, you have some damage. You have some damage, so you're losing some communication between the atrium and the ventricles at the AV node. So look at this thing. This is a good one. If you look at AV nodal delay, okay, here it's like 2 of these units. And then we have this. Okay, look at it now in this next one. It's longer, right? Like 3 or 4. Look at this next one. Again, this is the AV nodal delay. Now look what it is. 1, 2, 3, 4, 5. So we're starting to lose communication, and what will happen then is all of a sudden, here's a P wave, drop QRS. You basically have lost a beat, because now you kept separating more and more and more the signal between the atrium and ventricle. The AV nodal delay was okay, and then it got bigger and bigger, and finally it got so big that you actually lost a beat. And then usually it can reset. Okay, so a lot of times on heart blocks, if they're not that severe, you sort of can live with them okay without having to get a pacemaker put in and try to correct this. Especially this one. The other one was sort of a complete one where you start losing a lot of those. here was one that I like to see because it actually says drop QRS too. Does everyone sort of see this? You have P, QRS, but the P wave is getting further and further away, and so eventually you have a P wave. It doesn't actually reach, the message doesn't reach the ventricle, so you lose a whole beat. But then if it's like this, you know, you can, it's not that severe.
On there, is there an SA nodal delay?
There is a no.
Is it
So-
just AV nodal delay?
It's the, yeah, because this was the SA node firing and then signaling. You know, again, I should put that other one back, you know, quickly. But let me just should make another copy of that. So put this. So the SA node is firing and spreading through the atria, through the internodal and the atria. That's what this is. But then we had, I said it slowed down here at the AV node. And that's the AV nodal delay.
Okay.
So there is no SA node. If the SA node isn't working, then you have this idea the AV node will start being the pacemaker, and it only goes at 40 to 60 from that slide, right? So this one is like the SA node's working, but we have damage usually in this region right here at the AV node. So that all of a sudden, instead of having the normal block, you know, delay, it's getting more and more, and we're losing the ability to signal the ventricles to contract. And so you see this sort of, you go back, I have to go back to it now, but you saw it on that thing, and I'll go back, where it got bigger, bigger, and bigger, and eventually it never really reached the ventricle at all. And so you lost a beat. And then it resets. Don't ask me quite how it resets. I'm not quite sure. I'm sure I really understand that. Let's go back to that. So this one was a good picture, so I like this one. It's only one type. I'm going to show you the site to go to, and there's a bunch of other ones. Again, we're not going to memorize all of them, but for your interest, you know, they talk about a lot of different heart blocks. But mainly the ones, you know, are the ones I want you to know are the ones I'm showing here. So second degree one is the one I want us to recognize. You see a longer delay, and then finally a drop beat. So two more. And then I want to rest a couple of minutes and see where we are. Think a minute. So, ventricular fibrillation. Where's my thing? Hang on a second. Let me write it up here, maybe I'll remember. Flutter. I gotta remember to see what causes a heart flutter. But this, it might be just a less severe case of this. Here's ventricular fibrillation. Does that look good at all? Okay? So this is where we had that little train guide. The idea is somewhere, instead of doing the normal communication, we start having cells spontaneously itself kind of reaching their action potentials and causing these little contractions of cells. So you're not going to actually have actual contraction of the ventricles. You're just having what they call these ectopic, you know, in the wrong place, focus or foci. But the idea you're going to have basically different parts of the ventricles basically on their own just causing electroactivity. And so now the heart's not going to pump out at all. Okay, you're not getting hardly any or really any ventricular contraction here, and so that's bad. And of course, if we don't correct that, so you're going to use a defibrillator, which just resets it to the SA node, and then if it's okay, if it works, and so then you get normal rhythm. Otherwise, what's going to happen in this line? Death. Yeah. Yeah. Yes. And so once the pacemaker cells reach their thing, they literally through the gap junctions spread it out to the contractile cells, and the contractile cells then contract. The electroactivity is really the culmination of all of it. So it's the contractile cells basically, because that's creating most of the electricity. Just like your EMG wasn't the somatic nerves going, it was all the muscles. So yeah, that's basically the whole depolarization of the atria and the ventricles, but that's the muscle cells. But yeah, they initiate in the pacemaker and then spread out to via gap junctions, that's why it's fast, to the muscle cells. last one. Okay, and when you have a heart attack, there's actually, again, EKG stuff, there's like courses on it. You can look online and you'll see all kinds of stuff. It's really complicated. I'm just trying to get us a taste. And one of the things you often see when you have a heart attack is you have damage to cardiac cells, right? They're not getting enough oxygen. They're basically becoming, so that's hypoxic, and they're becoming damaged. And what you normally see are one of the things you see, I just want to make sure we say this, is this. Where instead of having a normal heart rate, okay, in which, do we have a normal one up there, in which you have sort of a baseline, here's your P, okay, and here's your S to the T, is on the same line. Everything's on the same line. Look at this one, okay, here's our QRS, and then from S to the T, it's elevated, instead of being down where it should be. Okay, and you can kind of look at this picture too, kind of the easy one. So you have this elevated S to T. And that's just due to the damage of the electroactivity trying to kind of go through the ventricles, but and repolarize. So it basically has caused this. Again, don't ask me more than that. As far as EKG is very sort of complicated. But this is what you associate with having a heart attack. Okay, that you can see some damage, and that's one thing. If you have one or you think you're having one, they go in. That's one indication that you might have a problem there. Besides looking in your blood for various things. So myocardial infarction or heart attack and an elevated S to T. Okay, so you have, this is QRS. Instead of being down here, it would be kind of like that. S to T, elevated. I don't know if that's better than that. Any questions? Okay, take a couple minutes to breathe and talk. We're going to do a little bit more.
Well, I didn't probably want to read because I do have a quick question. Let me actually try that and gather. Right. Okay, so right here, when like in the beginning of lecture, when you have the NA plus going in from the PCF to where I don't even know how to verbalize it.
You're blocking it from, you're not as much as
This is going in here. Well, is that right? I just want to ask what I would know to drive the
because the sodium is basically, sodium has to pump to what the sodium? What is sodium getting pumped?
It's bringing them in.
This is sodium has to pump sodium out. You gotta do your circle a lot. Remember, you have normal nerve. Normal nerve.
You said we'll add them, so we'll probably.
3 out to 2 in.
You're pumping sodium out. That's why, and potassium in. 3 out to 2 in. But you're pumping it out.
Okay.
So by doing that, what do you have inside as far as sodium? High or low?
Hi.
You just pumped it out.
Inside the cell? What are you asking me?
Yeah.
Okay, so you need to pump this out.
So what if you pump it out? What do you? How much do you have? A lot of sodium inside the cell or low? So we have low sodium. Okay, that's what sodium or potassium. That's what the sodium potassium pump did, right? Pump sodium out. So do we have a concentration gradient? No. We just do now, right? We have because if we open up a channel, sodium would go which way? In. So let us have it where we're going to have a transporter that's open to sodium. Sodium is going to go in, down its concentration gradient. Now what that's going to enable us to do is to pump calcium out against its concentration gradient. So whenever you're going against, you need energy. So instead of having just like a pump that just pumps calcium out like we do for the sarcoplasmic reticulum, we just have ATPase, we have a double system here. The sodium potassium pump creates the gradient, so we have low sodium, and now we have this this transporter, which now sodium goes, like again, we're like putting water in the dam, we open it up, sodium flows down now back. That energy is driving, think of like a wheel, driving calcium out.
Okay.
Does that sort of make sense?
Okay. Yes. Let me write it down.
Yeah, look at it. Okay, so we have just a little bit more. Promise you. So, and we're gonna end in 10 minutes basically without questions. Okay? So but don't forget this, because we're gonna add stuff to this. So first of all, I want to show you probably have this sort of cardiac cycle here. You're not going to have to know specifically, like there's the purple for the P wave. I just kind of look through this for a second. I don't find this that helpful, and here they put atrial contraction kind of where it is. We're not memorizing that, but you can see kind of this idea. The P wave was depolarization of the atria. That's followed kind of by contraction here. Then you have, and again, I don't care that you know, hey, that's Q going down. That pathway, it doesn't matter to me. Okay. And
So,
again, they have that.
On the board, that's a regular heartbeat?
Yeah. Well, for me. But I mean,
yeah.
that's a regular heartbeat. So the bottom line is, I don't care too much about that. So if you like that picture, fine. So we know all this, right? Diastole, systole, heart sounds. So wake up for a couple more minutes because I got something exciting here. Because we're going to add, we're going to add some stuff to this. When I do chapter 15, actually next time, so Wednesday is my second favorite day of the semester. Second favorite day of the semester.
What's your first kidney?
Oh yeah. Okay, but this is going to be incredibly cool. What you're going to learn next time, we're going to fill up this board. And you're going to see how we control blood pressure second by second. If your blood pressure rises, okay, and as you breathe in and out, we're going to find that changes your blood pressure. You're going to see this whole reaction on the board, what happens to your heart rate, what happens to contracting of the heart, what happens to your arteries, what happens to the veins. And you're going to understand completely how beta blockers work, alpha blockers, all this stuff. It's going to be really good. But right now, this is not bad. So we have all this. Now, we already have all that, so we got it. We're going to look at this figure. And there's a couple places, we're going to go through this whole sort of heart contraction and relaxation. And we're going to start sort of at the end of diastole. This is diastole. But there's going to be a couple important points here. This is really important. If you look at diastole, again, the whole idea of diastole was, it's not like, the atria fill and then the ventricles fill. During this diastole, starting here, the valves are open, we're filling from the bottom up. So blood's coming in, and we're filling. Okay, then you're going to have the atrial systole, which is going to be topping this off. Maybe 25% or so, I think, of the whole amount of blood in the ventricles we're going to pump out come from the atria. The other 75% have been filling up the entire time, but we topped it off. Now the next one, this is what becomes important. I mean, these are important, but this is what I want to focus on. Okay? As soon as we do that, the ventricles are going to contract. So, the ventricles are going to contract, right? Now, at the very beginning of contraction, before any blood's pumped out, when we're just beginning to contract, okay, no blood is pumped out, so that's why it's called isovolume. But what's going to happen at the very beginning of a contraction? What just happened there? Well, put it this way. When we begin contracting, do we want blood to go back into the atria?
The semilunar valves close.
Not the semilunar.
Oh, AV.
AV valves close. And so the very beginning contraction, isovolume ventricular contraction, is going to correspond to the AV valves closing. And what are we going to hear? Love. First heart sound. So those three go together, but guess what? We can put them somewhere on here. So where are those three events? I'm looking. Where is isovolume ventricular contraction in relation to what we're doing here?
After the AV nodal delay?
Basically, it's the where's the very beginning of a contraction according to us?
R.
R. That's it. right?
Oh, so-
R is the very beginning of contraction. That's where we start contracting. Isovolumic ventricular contraction represents the very beginning of contraction before we've ejected blood. And at that point right there, all three of those things happen. So in R, and again, I'm going to run out of room by the way I do it. R is going to have those three things. They're all related, but R represents, again, the very beginning of contraction before we change volume and we just have enough pressure to shut those valves. That's happening basically right at R. And so that represents, it's not the whole thing, right? It's the beginning. Just I have to write it out here. It's R itself. That's going to be, again, it's, I just write those words up there, but I'm right, because you can't read this. But that's the isovolumic ventricular contraction. Okay, which is up there. That corresponds to the AV valve shutting. And that's the first heart sound. Okay, that's R. Okay, so and if you look at this figure, maybe we'll put up later. There's a figure, if you actually look in the book, called this Wiggins diagram that has like a lot of stuff on one page, and there might be slight variations. This is sort of my simplified Wiggins diagram called my Berg diagram. So it won't be as complex. But if you read the book, you'll see kind of like this. But does everyone sort of get this? The very beginning of contraction is R, because that's where we started it. That's the very beginning. At the very beginning of contraction, we haven't pumped anything out in the arteries yet, but that pressure closed the AV valve so we wouldn't have backflow, and that's when we hear love. Okay? As we contract more, we of course are pumping out blood. Okay, so we've done systole. Now what do we want to do? We need to,
Diastole.
okay, now at the very, very, very beginning of relaxation or diastole, before any other blood started to come in, the very beginning, right when we let off that pressure, a little bit, what's going to happen? Do we want the blood we just pumped out to come back?
Semilunar valves closed.
And we hear,
Dub.
okay? So, isovolumic ventricular relaxation, the very, very beginning of it, is just when we relieve enough pressure so that the semilunar valve shut, and that is second heart sound. And where would that correspond? Here.
The end of T.
Yes. Okay? Because that's going to be the very, very beginning of diastole. Okay? So the beginning of relaxation here, before it starts filling, because then it's going to start filling, that's what's going to happen. So I'm going to have to put that up here now. But T, so R and T, R and the end of T, are like a lot of, we can correlate a lot of events. And so I'm going to put this up here. But T represents all three things we said here. And we're going to be done after this, by the way. This is isovolumic. Unless you want to do another 20 minutes.
Nothing.
So again, all three things that correlate with that. This is the end of T. You know, hopefully you have a better figure. You'll be redrawing it on your whiteboard 100 times anyway. Isovolumic ventricular relaxation, which again corresponds to what two things? And second heart sound. Semilunar valves shut, and we hear dub or the second heart sound. Believe it or not, next time we're going to add one more thing. I have to draw this, a little bit smaller. One more thing that's going to correspond to R and T, and then we're sort of done with that puppy. Okay? Is this pretty good? Yeah, you have a question.
That's one of the, yeah, I like T is the dub.
T is dub. Second heart sound. T is dub. And R is love. Love dub.
Cool.
Okay? Intense. But next time, even better. Next time, I don't care what kind of food, drugs, drinks that you need to take. I need you up for next time. Okay? Take off work. Okay? Relax and be ready because you're going to learn again, it's going to be our first real systemic thing, okay? We're going to fill up the board, but you're going to really understand blood pressure control second by second, and that's going to set us up later for drugs that are going to change this, okay? Beta blockers, calcium channel blockers, all stuff which has relevance for most of us, especially you guys. So we're getting better and better, guys. It's going to be more and more fun.
Fun.
Until you take the test, it's fun, and then it's like, you
I know more
know.
stress in our lives.
But the knowledge is so cool, okay?
Yeah, it is.
This is good stuff. You're going to like the cardiac.